Well, this is day 2 of applications of trigonometry, non-right triangle trigonometry, although it does have some right triangles in it, but it always has non-right triangles as well. And it is the last day of our first unit on trigonometry. So triangle trigonometry is what we've been doing, and this is the last day of this. And it's going to be shorter. We're just doing one example. These questions are different from the ones we were doing yesterday. They're, I think, really interesting, at least in what, once we realize their implication, I think it's really neat. Okay. What's different about today and possibly easier, I don't know, that's going to depend on the person, I suppose, is the diagrams are given. Okay. So you can see here our first question has a diagram and all of the practice. The diagrams are there because trying to explain these with words and then draw them yourself will be difficult because these are all 3D or at least most of them in the practice. The one we're doing right now and most of them in the practice are 3D. So there, you can see that one of the triangles in this diagram is lying down and the other one is standing up. Okay, that's what we mean by 3D. So the diagram is given, and so you don't have to do that part. Okay, now, but otherwise, we do these questions in the same way. It's still got 2 triangles and we still have to do some problem solving. We talked about sort of 3 different strategies, 3 different approaches that you might take with your thinking on how to solve these. And those same strategies will apply. Okay. In this case, for example, it's asking me to find the height of the tree. So that is this length, and I will call that x. Okay. And x goes from the top of the tree to the bottom of the tree, like that. And I am given most of the information. This is the triangle that's standing up, that x is in, but I'm given most of the information in the other triangle. And so it is similar to the ones that we did yesterday where we have to do some problem solving. So again, those strategies are thinking about the information you're given and what you can find with it. That's one of the strategies. Okay. So I could even ignore this entire thing and just look at that triangle and just say, well, what could I solve for, right? That's one strategy. Another strategy is I can ask myself, what would be useful in this triangle that's standing up? What measurements do I need that I don't have that could help me find what I'm trying to find? And hopefully that's something that we know, that in a right triangle, okay, to solve for a side length, you need an angle and another side length. And to solve for an angle, you would need 2 side lengths. In fact, I'm just going to talk about this a little bit further. So SOHCAHTOA, I'm just going to do the so, that's sine theta is opposite over hypotenuse. Okay, so this formula has 3 unknowns. Okay, it's got theta, it's got the hypotenuse, which is a side length, and it's got the opposite, which is a side length. And any 2 of those will allow me to find the other 3. So if I know theta and hypotenuse, then I could find the opposite. If I know theta and opposite, then I could find hypotenuse. And if I know opposite and hypotenuse, I could find theta. So to find a side length, I need another side length, not necessarily hypotenuse, one of the 3 side lengths, and an angle, okay? And that type of thinking works for sine law and cosine law as well. It's not exactly the same, but it's similar, okay? In that you can identify the variables that are in there, and you need a bunch of them, and then you solve for the other one. But for sine law, or for SOHCAHTOA in general, if I'm looking for a side length, which I am in this case, I need an angle in that triangle, which we have. Okay, we need the right triangle to tell us it's SOHCAHTOA. And then I need one other length. Okay, having another angle won't help me. I need another length. Well, there's 2 other lengths in this. There's this one and there's this one, right? And so if I could find one of those lengths, then I would be able to use SOHCAHTOA to find x. So that's strategy number 2. Strategy number 3, and again, you're probably going to use a mixture of these 3 strategies. Strategy number 3 is look for lengths or angles, side lengths or angles that the 2 triangles share. So that is this side length in this diagram that is in both triangles. And would you look at that? That was one of the side lengths. If I found that, I would be able to find x. So now I'm starting to think that's what I want to find. And again, at that point, if I get that far, I could just visualize. I'm only erasing it to visualize. I could just visualize this bottom triangle and ask myself, can I find that side length and how do I do it? Right? And now I'm starting to develop a plan. Even if I don't have a full step-by-step plan of I'm going to do this, then this, then this, I at least have a general idea of what I'm going to do to solve this question. Okay, so those were the 3 strategies that we talked about. Now, before I continue, because we already have an idea about how we're going to solve this one, I just want to mention briefly why I think these questions are so interesting. The implication of this question is that there's a tree on the opposite side of a river or a stream, or it could be anything, right? It could be a cliff, a canyon, um, a lake that you can't get around, a road that you can't cross, like anything that you can't get over, or easily at least. Um, and you want to measure the height, or you want to measure some length that's on the other side of, in this case, of the river, right? Um, and Uh, if I could cross the river, then maybe I could measure straight up the tree, but or maybe the tree's just too tall and I don't have anything long enough to measure up that way. This is a way that I can figure out the height of the tree and calculate it. And if I take my measurements carefully, I could get it very reasonably accurate. And as I said, in this case, I don't even have to be able to get to the tree. I can be whatever distance away from the tree that I want. Now I have to have some tools that can take measurements. And a long time ago, people who were surveying areas and determining heights of mountains or heights of trees or anything like that would have been using similar geometry, trigonometry to what we're about to do. These would have been strategies that people actually used. Nowadays, we have tools, lasers, that kind of thing that can take these measurements. But those lasers are often doing math, possibly, or some of those tools are doing the math um, that's involved in a question like this. They're just doing it as part of their circuitry, right? So even if we don't see it happening, there is going to still be elements of this sort of thing happening in measuring heights of tall things or inaccessible things, that sort of thing would still be similar to what we're about to do. But I just think it's really interesting that even hundreds and hundreds of years ago, before they had any of these kinds of tools, that with some simple measurements that you could take, and if you did it carefully, even with just a protractor and measuring tape, something like that, you could get a reasonably good measurement of, in this case, the height of something, a tree or something like that. So I think it's really neat. So what would you do? Well, you would start as an individual, you would stand here, okay? And you would measure the angle to the bottom of the tree. Then you would have to make sure you walk along the line, and that would be parallel to the river. Then you to some other point and measure the angle to the same point at the bottom of the tree from that new position. If you would also have to measure the distance between those 2 points where you took the measurements, all those measurements happened on this side of the river. You would also take this angle, okay? I don't know if you can see that. This angle here, you would take its measurement, and again, that's from the same side of the river, but now you're measuring to the top of the tree from where you're standing. And whoops, and with those 4 measurements, you could calculate the height of the tree. So I think that's pretty neat. And as I said, you could be on the other side of a canyon or something like that, and this would still work. So let's get into it. Let's do this, and then you can try a few on your own. Um, we've already kind of determined that this is the side length that I want to find. So I'm going to call it y. And I am going to use the three measurements in here, which means it's a non-right triangle. So we're doing sine law or cosine law. And this is where I have to decide which one I'm using. And everybody's going to do this in a different way. So you're going to have to decide how you're going to do it. Okay. There's lots of different ways you can do it. I've said this before. My favorite is I look and I decide, is this cosine law? And if it's not, then it has to be sine law. And cosine law is if I have all three sides. Well, I don't have all three sides, that's for sure. So it's not that cosine law. And the other one is if I have two sides and the contained angle. I only have one side. I don't have this side. If I had that side, I would have two sides, 1, 2, and the contained angle, and I could find y. But I don't have that. That means this is sine law. Okay, 100% it's sine law without a doubt. Now, I don't have, for sine law, you need to have an angle and the length across from it. And I don't have that currently, right? I don't have the length across from 35. I'm looking for the length across from y, and I have this length, but I don't have the angle across from it. But hopefully we know, and we see this easily, this is something that's important to notice, sort of quickly right away, is that if I have two angles, I can determine what the third is by doing 180, in this case, minus 35 minus 40, okay? And that's gonna give me 105, and I am gonna pencil that in, 105 degrees. And now I do have an angle and a side length across from each other, okay? So for y, I'm using sine law, and I'm solving for a side length. So a is going to be my y over sine of the angle across from it, which is 40, equals b, which is the 40 feet. You don't need that unit, but I want to show that the 40 feet is different from the 40 degrees. That's kind of a bad setup, that they're both 40, okay? And then over sine of the angle across from it, which is the 105 that we just found. Rearrange, 40 sine 40 over sine 105. And let's do that on the calculator. 40 sine 40 bracket. Again, always make sure you're in degrees, divided by sine 105. 26.61851, keeping 5 decimal places for now. Now I've got that y, and now I can move over to the other triangle. I've already kind of put this together that with an angle and a side length, I can find another side length using SOHCAHTOA. So 4x, and I'm going to redraw this because it's a useful strategy, but also because I'll have it on my screen, so I don't have to flick back and forth. But primarily, I want to do this because I want to remind you that this is I'm going to do that a little bit better, a useful strategy, okay, to use. So this is going to be the 50 degrees. The height is the x that I'm looking for, and the y is the 26.6 is this length here. So there's my hypotenuse. Now I'm doing SOHCAHTOA, right? There's my opposite, and the last one is adjacent. Which one is opposite and adjacent? Tangent. So tan of 50 equals opposite, which is x, over adjacent, which is my 26.6. But again, I've got the exact value on my calculator that I'm going to use. So times, and that keeps that full answer, tan of 50. And I got 31.7. Now I'm going to round to 1 decimal place. Therefore, the tree is 31.7, and that was feet tall. Okay, so that's 3D applications, day 2 of applications. Like I said, they're not that different from the ones that we were doing. In fact, some of you might find them easier because the diagram is going to be given to you. You will notice that some of them are going to be similar, but some of them are going to be different. Okay, so they're going to give us different measurements, or the diagram is going to be a little bit different, but I'm looking at these and a fair number of them are similar. Um, and this one's not, in this case, isn't even three-dimensional, but the diagram's still given. Okay, and so that does make it easier, but it does mean everyone might be a little bit different. But it's the same kind of thing where you've got two triangles and you're going to have a couple of steps, and so there's some thinking and problem solving involved. Okay, and as I said yesterday, what I really want you to focus on and remember is that you've got these strategies, and problem solving is hard if you don't have specific tools that you say, I'm going to try this. I'm going to try this. If you're just staring at it, hoping for the answer to come to you, that's when people start to panic or get overwhelmed or think they don't know what to do. There's no magic to this. There's just different things that you can try. And even if you're not sure if it's going to work, you have to be willing to try something and try strategy one. That's not working for me. I'll move on to strategy two, that sort of thing. Okay, so I want you to focus on that while you're doing the practice. Um, and again, if it will be harder at first, but it's like anything, after you've practiced it a bunch of times, you'll get better and better and better at it. Okay, so good luck with that. Keep those strategies in mind. Use this example as a model for what you've done. Um, and there isn't, as I said, there's not any more magic. One of those three strategies should be what's required, or a combination of two of them should be what's required to solve each of these problems. Okay, so try to stick to those. Uh, if you're really stuck on a question, you can skip it and move on to another one and come back to it after. Okay, good luck.